Thank you very much for the warm welcome, and thank you for joining my talk about our journey from a data warehouse to a data lakehouse. Apparently the clicker went missing, so don't be confused if I have to move it a little bit more. But without further ado, a little introduction of myself. So hi again, I'm Jan. I'm the technical director at Just Track. I meanwhile work in this industry for over 20 years. Focus most of the time was backend and infrastructure. So my main languages were PHP, Golang, Java, especially when it comes to the, to the big data tools. And infrastructure side, I have a lot of experience with AWS, Kubernetes, observability stack, and also databases. Especially here, I have a quite good track record when it comes to evaluating, testing, and running these things. So if you want to talk about databases, feel free to approach me afterwards. Then, what is Just Track? We are a mobile measurement platform and automation. We are based in Hamburg. So we are providing tools for tracking, analyzing, and optimizing marketing campaigns. So we are free to use. So if you're an app or game developer, sign up, give it a try. It's awesome. So what do we spend our time now? First, I want to give you an overview, introduction about data at rest and what solutions are available there. And then I want to talk about when and how we use them, and especially more important, and I guess also more interesting, how and why we switched between those solutions. And at the end, I want to give you a little bit more detail into our latest switch, which was then to the Lakehouse. So what is data at rest compared to data in use? So one thing we're tracking are clicks on advertisements. And we need to store those clicks for 30 days to be able to attribute them to installs. After 30 days, they lose their value, and we can delete them. So we basically have them in use for 30 days. And we want to delete them because storing these billions of events like in a high-performant lookup database is quite expensive. We have really high data volume there. But even after 30 days, you don't want to get rid of those completely, because even after 30 days and even after years, they are still producing insights and value for your business and for your company. And for this data at rest, the industry came up with different solutions. One of the earliest ones was a data warehouse. So it's quite similar to the relational databases you all love and know. For example, MySQL. So it's asset compliance, you get your autosymmetry, your consistency, your isolation, and your durability. And they are full CRUD compatible, right? You can create, read, update, and delete data. It also enforces a schema. And with schema enforcement and the asset compliance, you get really high data quality. But the drawback is those systems are quite expensive, especially if your data volume is really high. That's why roughly 20 years ago, companies started switching to the data lake pattern. Here the cost is pretty low, that's why they switched basically, but that comes with a drawback. You have no asset compliance anymore, and they're only supporting basically creation and reading of the data. You so don't have this update and delete anymore, at least not in an easy way. And they have a flexible schema, which also brings then the data quality down again. That's why, since a couple of years, they are now moving on to a new one, like the data lakehouse, which is basically trying to combine the advantages of the warehouse and the data lake without the disadvantages of the low data quality. So you get asset and CRUD back. You have, again, an enforced schema, so the data quality is quite high, but the costs are still low compared to the warehouse. So let's have a look at least one fundamental difference between warehouse and data lake. And that's how compute and storage are used. So for a warehouse, compute and storage are linked. So basically, every warehouse node is like a single database instance. So if you need more storage, you add another node. But you don't only get the storage, but also the additional compute unit. And sometimes you just want the storage. You don't need the additional compute, which is then just idling and increasing the costs. That's why for the data lake, this compute and storage got decoupled. So now you can scale both of them independently. Especially the storage layer got way simpler, like with the rise of the cloud providers, because usually you're just using some of the object stores to put all your data there. So if you have more data, you just put it, for example, to S3. And then basically if you want to read the data, you have to connect a compute engine to it, you read it, and like once you're done, you can like in theory could shut it down again, which makes it like way more scalable, cheaper, but also as this is now decoupled, it's way more flexible because you can use different technologies for storage and for the compute layer. And you cannot use only different ones, you can also exchange them quite easily. And especially for the compute, you can use also multiple engine solutions in parallel. So that's a super flexible stack. So let's have a look at that stack. It has multiple layers, like on top you have your analytics tools, your notebooks, your dashboards, your ETL tools. And these tools are talking to your storage engine. That's the catalog. This is where your tables and schema are stored, and your compute engines. The compute engines are like reading and writing the raw data files to your lake storage. So popular file formats are here Parquet, Afro, or even plain JSON files. And yeah, like I said, for the lake storage, the object stores from the cloud providers are quite popular, but also sometimes you still see like a good old Hadoop file system. So now with a rough understanding of like what a warehouse and a data lake is, let's have a look at the beginning of our journey. So when we started our startup journey, we started with something that we already knew. That was PHP, the Symfony framework, and we're using like a good old MySQL database and all that in a big monolith. So and even with our early scaling, at one point we were already using the biggest database instance AWS had to offer. So, and even with this big database, if we were running a little query, like for example, hey, give me the clicks from yesterday, the count, like it could render the instance already like unresponsive for seconds and minutes. And I mean, you can't do that with a production system, right? So that's why we started integrating Redshift. That's basically the managed warehouse service from AWS. And at the beginning, there was nothing automated, like it was just like manual copy commands to get the data from the MySQL database to Redshift, where we then could run our analytical workload. But also due to this manual trigger, the data freshness was not really good. So we had scaling issues. We were not happy with our warehouse, which basically triggered our first fundamental shift. So we did basically 4 things. You are not happy with the scaling, you change your monolith to microservice, you're not happy with the performance, okay, maybe don't use PHP anymore. So we started to using Golang. And we started to implement a data lake. And we did that like with only using managed cloud service from AWS at the beginning, which basically brought up to this. So you see a bunch of services, like on the left, you see ECS, where we had our Go applications running. Those applications were publishing the data to SNS topics. And from there, we had a serverless Lambda function subscribing to those events, pushing that to Kinesis data stream, which is like similar to Kafka. And from Kinesis, a Firehose was picking up the data, transforming the data into Parquet files, and writing that to S3. So once we had the data in S3, we were mainly leveraging Athena to query the data with schemas and tables, like basically the metadata stored in Glue. Every once in a while, when we had to run like schema migrations or had to run ETL jobs, we were starting an EMR cluster, so the Elastic MapReduce from AWS, to get a Spark cluster to do like more advanced things with the data. As you can see, there are quite some services, quite some jumps the data has to do. It was quite expensive with like more scaling. So the first thing we did was removing the first 2 things, like getting rid of the SNS topic. I mean, SNS in general is not really built for high volume data, and like removed the Lambda. So we cut some corners. Now basically our applications were writing to Kinesis directly. Still, for us, I mean, this works, I guess, well for a lot of companies. I mean, it's scalable, it's fully managed. You don't really have to do a lot with that to keep it running. But still, for us, it was too expensive. I mean, too expensive. Usually the trend is, hey, just use the serverless cloud provider, right? And we have the saying, buying beats building. So if you can buy a solution, you should not build it your own. But for us, this is not always true. At JustRec, we have something that we name like the bytes to dollar ratio. So we always have to look how many bytes we have to process to earn a dollar. And as we are a tracking company and have a lot of data to track, this ratio is quite bad. And we always have to be careful that basically our cloud infrastructure is not eating up all our profits. That happens quite fast, to be honest. So that's why we started to replace some of these managed services with open source solutions, which we are then now building, managing, and running ourselves. And yes, at the beginning, there's a little bit effort involved, and then it's more expensive. But after a while, once we have it running, it gets cheaper than the cloud providers. So we were going self-managed, which means the first thing we replaced was the Firehose, which was still the most expensive part in that stack, with Apache Flink. Apache Flink, stateful stream processor. If you don't know it, check it out. It's a little bit more complex to operate, but you can do really powerful things with it. Like, check it out, it's really cool. And then the second thing we replaced was the Kinesis stream. And replaced that just with Kafka. I guess that all of you know. Still one of the most popular message brokers. It just scales, it fulfills our scaling needs, our performance needs. So we had our stack also running for a couple of while, but it really never was fun. It always felt more like a bumpy road. And I want to share now why this road felt so bumpy. And I guess also those reasons hold true for a lot of companies which are implementing running a data lake, because that's just the drawbacks from a data lake. So reading is hard. I mean, it works well as long as you have SQL access. So if you use an analytical tool where you just punch in your SQL queries, I mean, those tools need, for our stack, Athena and Glue support. But I mean, AWS is quite common, so all major tools are supporting that. But if you're leaving the space, it gets a little bit painful. You start dealing with raw data files in an S3 bucket. You're also dealing with Parquet files. I mean, Parquet works well as long as you are in the Java ecosystem, because basically everything in there, also Parquet, is implemented in Java. But if you leave that, it gets really difficult. So don't try to do that, work with that with Go. That's not worth trying. We tried. Don't do the same mistake. And what also comes into place, once you want to do these schema migrations or running ETL jobs, you can't do that with Athena anymore. You need a Spark cluster, you need a Flink cluster. If you want to spin up those clusters on demand because you don't want to have them running all the time, that's a lot of operational overhead that you basically don't want to deal with all the time. So reading is hard, but what works even less good is mutations. So writing works good. Like I said, it's built for create and read. But if you need to change data, even if it's a single event or a single field of an event, you can't do that now anymore with an update or a delete statement, how you know it, for example, from a relational database. You need basically a compute engine, Spark, for example. You have to spin that up. You have to write a custom Spark script to do your actions you want to do. Then you basically have to reprocess your whole data partition. It's just not one single event, but it could be the whole day of the data. And you have to write it to a new S3 position. And then you basically also have to manually remove the old files and copy the new ones in. So there's a lot of manual file movement involved. Also, there's no schema evolution built in. So if you want to add or remove a column, you basically have to reprocess your whole data set to add that. So a solution to that, this tech stack for the data lake got a new addition, the table formats. It gets a little bit more complicated, but I'll explain a little bit more what the table format is soonish. But first, let's look at our target architecture. So that's the architecture that we are targeting. We still have Kafka. We still have S3, those two we don't want to replace, but everything else we want to reevaluate. And in the end, we are running everything in Kubernetes with GitOps. If Steve is still listening, yes, we're using GitOps as well. So the first thing you have to choose is basically which table format you want to use. So what is a table format? It's a metadata layer between your compute engines and the raw data files. So you basically don't have to deal with these raw data files anymore, which is super convenient. You also get your asset compliance back. So you again have like this isolation and consistency. And it's again like full CRUD operability. So again, with like compared to the warehouse, you can now update and delete data just with simple SQL queries in your compute engines, which is just way easier to operate. And those table formats usually support full schema evolution. So if you want to change your schema, you just do like alter table, add column, and it's done. Like you don't have to reprocess any data, which is I don't have to tell, a big boost. So these are some common table formats out there, like it's Iceberg, Delta Lake, Apache Pymon, and Hudi. And yes, there's also a service from AWS, S3 Tables, which is basically a managed Iceberg system. But as we want to move away from these managed services, this is not an option for us. And what we've gone with is Iceberg. Why? It has the broadest, widest support in the open source landscape. So basically, all major tools are supporting Iceberg. You can run multiple engines with it. It's also optimized for analytical workloads, so especially the workloads we have. It has robust schema evolution, and it supports time travel and rollbacks and versioning. And to that, I will come back at the end. So we have the first puzzle part, basically, for our architecture, the table format. So now we have to look what we want to use as a catalog, because that's what the format is talking to. So as a reminder, the catalog is basically the central registry for your schema, for your tables, where your data is located. So it's an abstraction layer on top of your raw data files. And it powers now like the discovery and also the governance of the data. So it enforces the schema to keep the data quality high. I've put here again some popular options. Like as I mentioned, we were using Glue, but also that choice like we want to reconsider. We don't want, as I said, don't want to use too much AWS anymore. Quite popular are still the Hive Metastore from the Hadoop ecosystem. But from my opinion, if you can stay away from all this Hadoop stuff, you should do it. There are also JDBC and REST implementations available. And then there's Nessie, with the best logo, from my opinion. And actually, we've gone with Nessie. Why? First, it's not the Hive Metastore. Talk to me later why I hate this stuff so much. And like it does one thing and one thing only. Like it really only stores your tables and your schema. And due to that, it's quite small. It's easy to operate, and it also provides some CLI tools for common operations you want to do on your Lakehouse. So for garbage collection, for compaction, like Nessie supports already here with some good CLI tools. And for this versioning and time travel, which I already mentioned, it supports Spark with some SQL extensions, which is quite nice. We can see that also at the end. So now we have our catalog in place. We have the table format. We basically now want to start writing data. So we need an ingestion engine. Here, one step back. You need schema first before you start writing. So you need an engine to manage the schema. We had Athena. Athena also supports Iceberg, but only for an old version. So, and yes, we don't want to use AWS anymore. Then, okay, we still have Flink in place. So we looked into Flink. But as I said, Flink is a little bit complex to operate. If you can avoid it, you should not do that. The same is a little bit true for Spark. So we looked for something else. And then we looked into Trino. And It's also, like for our users, quite good because it feels like a Athena, because in the end, Athena is just a managed Trino system. So we checked out Trino further. It's like easier to operate than Spark and Flink. Like it's only a couple of lines to get started, and it like has all client drivers for all major languages. And due to the JDBC support, you basically can connect all common database tools to it. So I want to share at least like one configuration file that's for Trino, how you have to set up basically the connection to the catalog and to the table format. So we are saying here, okay, the connector is Iceberg, the catalog is Nessie. You point it to the catalog URL, you point it to your storage location in S3. That's basically all you need. You can also configure the file format. Here it's Parquet and the compression. But yeah, as you can see, it's not a lot to configure to get started. So then you basically just use your favorite database tools. You start to create a schema. You start to create tables, basically the same stuff you know from Postgres or MySQL. And once you execute that, you can check like with show create table, okay, what has Trino done? And then you see something like this. Hey, yeah, okay, cool. I got my table, I like have my Parquet file format, I see a storage location, I can see also the partitioning I have provided. But if you look a little bit more closer, you see something like this. Like I tried to create the schema with like camel case, and Trino got back with me with like all lowercase. Like that puzzled us a bit at the beginning. And if you deep dive a little bit the documentation from Trino, you can find something like this. Identifiers are treated as not treated as case sensitive, sorry. It's indeed a little bit hidden. For me, I would have liked that a little bit more prominent position. I mean, in theory, I like that approach. I mean, why should be something like store ID with an uppercase I, something be different than store ID or lowercase? You would never create a table with those two columns, right? That would be a complete mess. So in theory, I like that approach, but it destroys the interoperability with other engines. So for example, Flink is not case insensitive. So then basically once you start writing with Flink into that schema, it complains the schema is not matching. So you can't basically do it like that. So Flink complains, then okay, let's use Flink to create the schema, then at least it's compatible. But then there was something like that in the documentation. Like it doesn't support adding, removing columns, renaming columns. Basically, yeah, okay, you can create a table, but then afterwards you never can change it again. That's, I mean, also a complete showstopper. So Flink also not an option, but then just brings us back to Spark. And here, luckily, Spark supports everything Iceberg needs. It's like the most feature-rich compute engine. And I mean, in the end, you will need Spark in all cases. If you want to run like ETL jobs or like more complex BI jobs, like you will do that with Spark in the end. So you will want that in your stack, nevertheless. So here's basically the same example again with Spark. Like the SQL syntax is a little bit different, but in the end, it's close to the same. And here you can see it like with the show create table, that indeed the schema has a camel case identifiers. So we have now also our schema in place. Now we need the ingestion engine. We have Flink already in place for our data lake. So like it works well for us. Why not to continue to use it? And luckily, with Flink, the ingestion is indeed quite easy. I mean, that's basically the lines of code you need to write from a Kafka topic into this Lakehouse now. So the first 3 lines is basically creating the Flink execution environment and creating the catalog with basically the same properties I've provided already to Trino. And then I can create my Kafka source, setting it to the clicks topic. I get a data stream, a source stream, and that stream I can just write to the sync table. And that's basically all you need to get started to write the data from Kafka to your Lakehouse. So also now ingestion done, cool, it works. Coming to the reading part. We have multiple use cases when it comes to reading. So, for example, we have a couple of Flink applications where we from time to time want to reprocess some data. So usually Flink is reading from Kafka, but if we want to reprocess some old data, we're doing that from our Lakehouse. The same is true for Go. Like before, that was like with the data lake, that was basically not possible. And for querying, like running this analytical SQL statements, we are using Trino. And when it gets a little bit more complex, we're using Spark. As I guess SQL statements, most of you know, I want to highlight again Flink and Go in this case, just to show that it's not a lot needed. And here's basically the same job for reading. Again, this first 3 lines creating the environment and the catalog. And then you basically can also just create an input stream with a SQL statement. And then afterwards, here I'm just printing it to the console, but you could do now with like whatever you want with the data again. The same example basically for Go. Like I said, with the data lake, we basically gave up to do this reprocessing directly from the data lake with Go. But with the Lakehouse, like it's super easy again. Also here, you just create the catalog, select the table, and then you can basically already start iterating again over your events. Like this was a really big game changer for us, to be enabled basically to do that again. Also here, there's an official library for that from the Apache, so like the Iceberg Go library. So this brings us then to our final architecture. Like we have Flink as still as the message broker. We have Kafka, as the message broker. Flink as the ingestion engine. Our main engines we're using are Trino and Spark, Nessie as catalog, and still S3 as object store. And like I said, everything running in Kubernetes, self-managed. So I promised at the end that I will talk a little bit about this data versioning and time travel. What Iceberg does, like for every operations you do, like is it an insert, an update, or a delete, it creates a new snapshot. And you can see here at the bottom, that's basically the snapshot metadata table from Iceberg, where you can see like the snapshot IDs. So at the top, like I did some like insert, update, delete statements, and like for everyone, you get a new snapshot. What you can do now is use the snapshot ID as version and provide it to your select query. So you can say, select all from clicks for version as of with this snapshot. So you basically can travel back in time and look for every operation you did, how the data was looking like, which is a super cool and powerful feature. And I mentioned this also with Nessie. Nessie has some cool support for this versioning and time traveling. They have that basically built in as a catalog. They're like calling that commits. So it's looking a little bit like a Git version. So you basically get here now a new commit for every action you do. And it gets even better. Nessie, with these SQL extensions for Spark, provides also branching. So you can create branches on your data. For example, you want to run a migration or you have to fix some data. You usually don't want to do that on your production data, where basically maybe all your BI jobs are currently working on. So you want to be a little bit more careful with that. And what you can do now with Iceberg and with Nessie, you can create a branch on your data. Here I named that def, so create branch def. And then you can now do all the operations on that branch. So you can here update clicks at def, so you provide the branch name. And then every action operation is done on that branch only. And you can also query like only that branch to check how the data is looking like. And once you're happy with your data, you can basically just merge it back into your main branch, which makes like operating on the data a lot easier than before, where you like had to do a lot of manual movement with your files and so on. It's a really powerful feature which just like brings a lot of convenience. So what have we done? At the end, we have a state-of-the-art Lakehouse. We use it like 90% with open source tools instead of like managed AWS services, which brings like the costs like even further down for us. And we have increased our operability and like convenience again. It's got a way like a lot easier again to work with that data. If you want to look more in how Iceberg is working or how Trino Spark is working, we have a GitHub project in our like GitHub organization. We call that Haus am See. I mean that's German for Lakehouse, where you can find basically our proof of concept we've done. So you get a Docker Compose file which you can just run, and then you get like Trino, Spark. All the tools you need to start working with the Lakehouse. You also find some examples for Flink, Go, like how to read and write data. Any questions?